Hey everybody, it's David late at night. It's 12. Today we'll be talking about one of the most important topics in computer science, at least for theory, is time complexity. Yeah. And essentially, it's a way of measuring time for computers or computer programs, and especially when computers are so crazy nowadays, where there's so many different ultra powerful computers, I don't know, gaming computers like in NVIDIA GTX 360 or something. I don't know. But computers have different processors and it's pretty hard to measure time in a consistent manner. With time complexity, we can mathematically figure out the amount of time it takes, not necessarily exactly, but kind of a function to represent how long a program will take. And as I kind of implied, time complexity is essentially making a function of time. There are different ways to do it. First, we've got big O notation, which is the most important one, which calculates the worst case. The amount of time where you're given the worst case scenario. If you're given the worst case. We also have omega notation, which is the best case. You don't have to know omega and what we call theta notation. What's more important is big O, average case. And as they look like, they are all functions. They're functions like in math, where it's commonly, you'll see in complexity theory books, it's kind of written like this. And there's a reason for that. Whatever function inside of this is kind of, it creates a graph like this. Like just a normal graph, actually. Whatever big O notation you have, it has a corresponding graph to it. And x is the amount of input. Okay, the input stays constant for every single notation. So, for example, would be if I were adding 1,000 elements to an array, x would equal to 1,000. Okay, x is not a range. Okay, that's my point. And there are different algorithms, and you'll see different graphs. For example, if I wanted to take, if I wanted to just for loop through the array, or I would say for I in x elements, or the, actually, instead of x, what we usually do in computer science, especially with big O, is we use big O notation. Or not big O notation, we use n. I just have x like in math. Mercy. Okay. And n is kind of representative of a lot of things, but more commonly it's known as the size of an array. So if I had an array of size n, right, I can do a for loop through every single index in the array. And maybe I would print out this is pseudocode, the index. And this for loop would run n times. Okay. And n can be any number. If I put in 1,000,000, this for loop is going to run 1,000,000 times. If I put in 10 times, it's only going to run 10 times. And this kind of makes a linear function. As n grows, f of n, which is equal to the amount of time, increases with it. Okay, and you'll notice that I'm measuring time by the amount of iterations in the for loop, right? If the for loop runs a lot of times, it's gonna, if the for loop has a lot of iterations, it's gonna take more time. So time complexity doesn't measure time in seconds. It measures time in operations. Okay, this is bugging me. Time in operations. We'll just call this op. Right. So, like I said earlier, your use of time complexity is best used to determine whether an algorithm is going to fit your time limit in a problem. And you're not going to worry about too much with beginner problems, but when you get to harder problems, that's going to be very, very important. So I guess let's just do some practice. That's a good way to kind of understand it. If I had for I in here, and for j, what would be the time complexity of this? Well, how would it work is, let's think, right? If I plugged in a number, how many times would my code in here run? So if I plugged in 10, right? Okay, let's calculate this, right? This for loop, this upper for loop right here, or actually I'll circle it. This upper for loop is going to run 10 times. And then the second for loop is also going to run 10 times. So for every time in the 10 times at the beginning, it's going to run another 10 times inside of it. And this is where we get multiplication. So when you have a nested for loop, it's going to lead to multiplication. Okay. And this is a O of n squared algorithm because it's n times n, right? N can be any number. So if I put in 1,000, it's going to take 1,000 squared operations, or 1 million. Okay, and then the graph corresponding to it, where this would be O of n, and this would be n, it's going to make a parabolic relationship, right? As n gets bigger, O of n gets, or the amount of operation grows exponentially. And yeah, that's all time complexity is. You'll get to some crazy ones like O of log n. And I want to make sure that this is not O of log base 10, but in fact it is log base 2. And you'll look, as like you're probably a beginner watching this video, but when you get to harder problems, 2 is going to be the magic number in computer science. But yeah. Before I leave, one thing I want to know, like to note, is measuring time complexity is going to be a skill that is going to take a lot of practice and a lot of getting used to. You're going to have to read a lot, you're going to have to practice a lot of problems, but time complexity is going to be one of the most useful, and it kind of helps with math and other subjects. You'll see, like, when you do like rate of change and stuff like that, when you think of like slopes and all that stuff like that and derivatives in calculus, it's very similar. It has a lot of similarities, which will help a lot. I hope you enjoyed. It's a very short video. Time complexity is not really a complicated topic, it's just misunderstood. Just remember, big O of whatever whatever function is inside, just imagine kind of like a graph where if this was n cubed, or yeah, it would make kind of like, it would make this. There's no negatives for n, by the way, but if like n was equal to 4, O of n, or n cubed, would be 64 operations. Something to think about. And whenever you do for loops, every time you nest it, you multiply by n. And yeah. Oh, one quick note, we don't have coefficients in big O notation. So if I said 3n, and like, for example, if I had a for loop that run like this is still O of n. We just take out the coefficient. And the reason for that is because it's not really as important. We only take the important elements, such as n. It's just, yeah. For example, if I had 3n squared plus n, this would be an n squared. The big O notation would be n squared because n squared is more important. So like as n grows bigger, this smaller n is going to lead to less significant numbers. Where if I put 1,000 for n, this would yield 3 million, while this would only yield 1,000 operations, and we only care about 3 million. Like if we have, yeah, we only take the biggest one. That's it for today. Hope you enjoyed, and see you tomorrow.